Hey guys, so in this video we are going to talk of the problem c8kbf. I don't know why they gave it such a name and tree. So the description is a bit long, but I'll try to tell you the problem in brief. So let me get started with it. I actually hope that you have gone through the problem once before seeing this video. If you haven't, I'll advise that stop the video right over here, go to this particular problem, check it out and try it at least once on your own. If you don't get it, then come back to the video. Cool, so let me get started with the solution or the approach. So before starting with the approach itself, let's talk about what the question asks us to do. So the question is saying that we have a unrooted tree. So by unrooted they mean that the root is not defined. So it's just an undirected graph that we have as of now. This seems to be an undirected graph, right? Now you have to select paths. So if you select any two vertices, let's say this is A and this is B, right? So in a tree, it's well known that there can exist only one path, right? So over here, this is a path. So let me change the color. Yeah. Okay. So this right over here is a path, right? So you can only go from A to B using this path or using this simple path. Now you have to select four nodes. A is less than B and C is less than D, right? So two nodes are these and two nodes are these, such that the XOR of the paths. So what do I mean by XOR of the paths? Let's say this has an XOR value A, this had B, this is C. So A XOR B XOR C. This is the XOR value of the path from A to B, right? So they want that the XOR value from the path from A to B and from C to D should be same. Now when you detect such vertices, you have to print the answer. If you don't detect any such vertices, you have to print -1. So cool enough. That is something we already understood. Now let's get started how we can do the questions. Also let's have a look at the constraints. So the constraints over here are that n can go up to 10 to power 5. Now if you are thinking of an n square logic, that is kind of bound to fail, right? Also the values for or the weight of the edges using which we'll be making XOR sum of the path that we're gonna take, that's actually limited to 2 to the power 20. Now this is a good thing. Now why is this a good thing? Because 2 to the power 20 is around a million, right? Now a million computations are easily doable in a computer. So a million basically is 10 to the power 6 because 2 to the power 10 is 1024. 2 to the power 20 is 1024 into 1024. That would be somewhere around 1 million or 10 to the power 6. So those many operations are easily doable. Now if these are the if this is the total states which I can have, or this is the total ways there could be paths in, right? So there would definitely be some overlapping. I hope that makes sense. If that doesn't, then I'll highly suggest you to read a pigeonhole principle. That's actually a easy thing to understand, but that's not the motive of this video, so I'll not be going over that. Cool. So what I'm saying is that let's firstly define that how you gonna store. So there could be any two vertices, right? A and B. Then they could let's say for all the vertices from I from 0 to n-1, let's call it I, right? And then from I plus 1 to n-1, let's call this J. Now the first thing is that I want to know what their XOR is. So let's say this was in this graph, right? In this particular graph itself, I want to know what the XOR value of this particular path is from A to B. Can I utilize some sort of data structure so as to store it so that in order of 1 I get this particular answer? So order of n is pretty trivial. I can start a loop from here, or I can start a DFS traversal until I reach to B, right? And then I can report that whatever the XOR I was getting, but this is going to be order of n logic. I don't want that. Now you can say that okay, we can store it in the array, right? Wherein you can have n elements and n elements. Then you can say that okay, so this could be I, this could be J, right? Fair enough, you can do this, but this again has a space complexity and time complexity of order of n square. We don't even want that. So what other thing can we do? So we can use a simple concept and yet a very elegant one. So this concept is actually called Prism exalt or pre-exalt or whatever you want to call it. It's just about the thing that you should know. It's the name actually doesn't matter. So what this states is that let's say this is a tree we are having. So let me draw the tree. This video might be a bit long, but I want to explain the concept in in a good detail, right? So the tree is rooted, but rooted or unrooted, it won't make any difference. Let me tell you why. Let's just populate it with some dummy values A, B, C, D, E. F. Okay, or E or F. Cool. And let's also give it some names. So let it be A, B, C, D, E. There's F over here and there's G over here. Cool, makes sense now. Now what is, or let me just write it a bit big, it wasn't even getting clear. So A, B, C, this was a F, this was a D, this is a E, this is a G, right? Cool. So now let's say what is the value from C to B. Now C is I've taken C as the root. Similarly, E could have been the root, it wouldn't matter. So I'm over here taking C as the root. You can take E and you can try to dry run it. It actually doesn't matter what you can take any root for that matter. So I'm taking C as the root over here. Now the node I'm taking as the root, from that I have to calculate the XOR of every other node. Now it's easily doable in order of n via simple recursive call. I'll not be explaining the basic stuff, but okay. So from C you are going to B, right? So from C to B, what's the XOR? So the XOR is A. What's the XOR from C to A? The XOR is A XOR C, right? So this gets calculated, this gets calculated. What's the XOR from C to D? It's A XOR D. This gets combined. What's the XOR from C to E? So it's B, right? This right over here. Okay, let me, yep. Okay, what's the XOR from C to F? So that would be B XOR, what was this term? Okay, so this was A, B, C, D. Okay, it had to be a E, I guess. Yeah. So it would be, okay, C to F is basically B XOR E, and C to G is B XOR F. Now I want to calculate. So now I already have the values, or I have the XOR sums or XOR path if I'm considering C as the vertex or C as the starting point. Now let's say I want to consider A as the starting point, right? So I want to calculate A XOR B. Then what would be the values? So I simply have to add these two values, or XOR these two values up. Now as soon as I do that, I get A XOR A XOR C, which gives me C itself. Let's test it. Is it correct? So yeah, A XOR B is calculated, it's corrected by a single edge that is having a weight C. But that could be coincidence. Let's test it again. So let's just say we want to calculate from B to E, right? B to E could also be a coincidence. Let's try something, something bigger. So maybe from F to G, right? So from for F to G, we'll have to take two nodes. So one would be C to F and C to G, right? Okay, let's take these two. So C to F is B XOR E, and C to G is B XOR F. We XOR these two things, right? B gets cancelled out. We are left with E XOR F. Right? Is that correct? Yeah. So this is the tree for F to G, and over here you have to go through E and F. Now, even a bit of common sense would tell you that why this thing is always true, but if I just have to make it more clear to you, the thing is that let's say there are two nodes A and B over here. Like these were two nodes I was having, right? A and B. Now they are connected by this path. That is this direct path. However, when I was coming from my ancestor or my parent, I was actually traversing this. So I was going through this path once. So I was going to this, then over here, right? And when I was going to B, I was going when I was going to D, I was going through this path. So clearly this particular path was getting included twice. So as soon as you get something that's being included twice in a tree, or in an XOR, right? So whenever you XOR the same quantity twice, it gets cancelled out. So this actually got cancelled out, and we were just left with the required edges, or the minimum edge required. So that's the proof for it. I hope everything is crystal clear till now. Now I'll be talking about how can we use it. So if you are able to do to this point, then things are actually easy for you. So this can easily be done by this particular construction, or calculating the values from C to B, or to C to A, from C to any other point, or from root to any other point can easily be done in order of n. I'll explain that in the code, but I just hope that you already know this thing. Now I can say run a loop from I is equal to 1 to n, right? And then run the other loop from j is equal to I plus 1 to n, right? Also maintain Hashmap. which already contains the values that I've already processed, right? So it would be containing, okay, from let's say I minus 1. So let's say we are currently at I. So the values we would have already processed. So this is what I'm talking about. So if you are at I if you are at a particular index I, so from 0 to I minus 1 you have already processed, right? And for all of these values you would have already also processed a j's that would be ranging from I plus 1. So let's say this was some index k. So for that you would have already processed j's from k plus 1 to n. I hope that makes sense, right? Because the loop is actually going from I plus 1 to n. Yeah. So these values I will already I'll actually store in a hash map. Now why I want to store these values? Because the question wants us to come up with two paths that have the same value, right? So if I've already seen a path that is having a value and I'm again coming across a path, then I need to flag it, or I need to say that, okay, I found a path which has the same value. So that's the reason of using a hash map over here. Then I run this loop. The only thing I need to check is that, okay, what's the, okay, so over here, how can I get the value from I to j? So I need to get the value of I to j, right? So I can say that the value is dp of, so the dp or the prefix exalt, let's call it. Okay, let me erase that. Yeah. Okay, so let's call it the prefix exalt. Now the prefix exalt would actually contain the values from root to I, right, and root to j. And this value would be, let's say if it was denoted by px, so px I would denote the value of root to I, or the XOR value from root to I, XOR with pxj, right? So this would give me the value or the XOR path from I to j. Right? I'll see that, let's call it val. Now if I've already processed to val before, or if I already have seen a path that was having the value val, then I found two paths, good enough. If I have not seen it, let's keep continuing it. But wait, one would argue that you are running loops from n to n, right? This technically becomes n scale logic. So have you lost your mind? Like, it's gonna give you a TLE, and yeah, fair enough, this would give us a TLE. The only thing is that before it gives you a TLE, before it does this 10 to power 5 into 10 to power 5 operations, it will actually stop. Now why would it stop? Because the possibilities for this value val is actually limited to 10 to power 6. Why is that the case? Okay, so the weight of the edges, or the values that you are seeing over here, that is a, b, c, d and so on, it is limited to 2 to the power 20, which is approximately equal to 1024 into 1024, right? That is approximately equal to 10 to the power 6. It's not approximate, it's exactly equal. This is approximation, right? So if you have 10 to the power 6 possibilities in total, as soon as even in the worst case scenario, if every possibility you're checking for is absolutely different, then also when you'll get to this number, or when you'll check for this particular possibility, that is, okay, yeah, so when you'll check for the 1 millionth one possibility, you'll find a match over there itself, right? So when you'll check for this possibility, or the Prism principle basically is that, let's say these are like 5 boxes, right? And you have, okay, these are not 5, okay, these are 5 boxes now. Yeah, these are 5 boxes and you have 6 chocolates, right? So one box at least would have 2 chocolates, right? That's the bare minimum, because like firstly you can distribute 1 chocolate in each, right? After that you'll be left with 1 chocolate which you have to distribute. So yeah, at least one box is gonna get 1 additional chocolate. So the exact thing applies over here. So even if you are able to come up with 10 to the power 6 unique possibilities, even in that case the next possibility is gonna collide with some other possibility that you have already calculated, and in that case you'll already have the answer. Cool. So I think that was a lot of introduction and how to proceed with prefix XOR arrays. Now let's get to the code. Okay, so this is actually the basic stuff. So firstly taking the input, and also we are talking about the one base indexing. So I'm just subtracting 1 from the node values over here. Yeah. After that I'll have to take I'll have to run a loop, or you can call it a DFS array or DFS loop. Okay. So what it does is it marks the current node as checked, so that we don't find ourselves going back to the parent. If you want to remove this can be done actually. So you just have to mention over here what the parent was, right? Initially it can be set to 1, and then over here Then you have to set the parent. So the parent is node. I have to say if node is not equal to par, only then do this. Okay, not node, but if x is not equal to par, only then do this. Let's test it out. Okay, it failed. Why it failed? Let me see. Okay, it's still relying on the visited, which we have cleared up. Cool enough. Let's test again. Again failed. We removed something we shouldn't have. Okay, over here. Okay, got it. Let's see. Okay, it passed now. So yeah, this is working code. So we just have to check that the parent should not be similar. So since it's a tree and it's not a graph, so there's no point of having cycles. The only way you can get stuck in an infinite loop is that from a child you're going to its parent, from the parent you're going to its child, and that keeps continuing, right? So the only thing I'm using is the parent, right? Now I'm saying that from the current node go to the next node, right? So that I can do. So that would be already there in my adjacency list. Over here x is actually the next node, so let's call it the next node. And okay, or let's just call it the child by ch, and this is the weight. Okay, so my child should not be the parent, obviously. Okay, and prefix XOR of child would now be whatever the prefix XOR for the parent was, or else node was, odd with the weight. So from A, you are going to B. So whatever prefix XOR A was having, that would obviously get continued, right? So even in the example, I explained the same thing. So that would get continued. On top of that, the current weight would get XOR. So this is how you do XOR in C++. Then I'm saying run the loop for the current child, right? Keep performing this. Let's make the code a bit more cleaner. So I can use remove this this particular vector. I can remove it from there itself, from here too. Okay, from okay, you can remove this. I think that should work. Yep. Okay, let's just remove the visitor from here also. That should be fine. Let's just remove it from here also. Yeah. So we reduce the time complexity and the space complexity by a bit just by looking at the solution. Cool. Then what we are going to do is that we are going to run two loops, and we are going to say if we have already calculated this particular value. Now let's make it a bit nicer. Let's just put it over here. Now understand that when I go to the solution post contest, I'm able to make a lot of modifications, and I'm able to make the solution look a bit more cleaner. So this is always advisable, no matter at what level you are, right? It's always advisable to go through your code post your contest, because in contest you'll most probably be writing code that actually doesn't make a lot of sense, or it's having a lot of redundant code, and the things are not in order. But as soon as you lose these things start getting better. Cool. Let's test it out if it's still valid, or we made some wrong changes. Yeah, cool. So what I'm saying is that the value, or the XOR path from I to j, it actually would be given by this, right? When I'm XORing it, I've already covered it in the explanation. Then I'll say if I've already seen this particular path, then I already got an answer. Great. If I have the answer, then I'll just print the values, or the a and b's for the previous path which we're having, right? Followed by I plus 1 and j plus 1. But if that doesn't happen, right, what should I do? So if that doesn't happen, just store the value. So the else indentation is a bit off here. So if that doesn't happen, then just store the value corresponding to this particular path, or this, yeah, the XOR path of this of these two nodes. Store the values I and j corresponding to that at the end, print -1. So it's as simple as that. Let's copy paste the code. Let's see if it works. Okay, we made some changes right now, so just wanted to check if the code is still fine or we broke something. Okay, it's running. Guys, actually the reason of not making videos for this particular problem, or problems which have a difficulty rating somewhere around 2000, is that not a lot of people like it, right? And there's not a lot of motivation to make such problems, and that's the entire reason. But if you guys actually like it, you can let me know. I'm always happy making videos that can help you out. Yo. So over here also we see a AC and it gets accepted. So yeah, that's it for the solution. Let me know if you found the concept useful. I also discussed the prefix XOR concept in detail. So let me know if that was useful or I hurried up a bit. I hope you this explanation actually made sense to you. If there's still any doubts, you can always let me know in the comment section below. Cool guys, bye bye.